Good evening, and welcome. Tonight, we are not just drifting back through time. We are journeying to its very edge, to a moment when the world we know, the world that should have been, was stolen. We are voyagers in deep time. Our minds are tuned to the scale of days, seasons, and lifetimes. But the story of our planet is written in a language of eons. We often think of the great extinctions as sudden, violent interruptions, an asteroid from a dark sky, a world flash-frozen. But the most profound catastrophe in our planet's history, the event that sculpted the very destiny of life, was not a singular event. It was a sickness, a slow, suffocating planetary fever that lasted for millennia, set in motion by a fire deep within the Earth itself. Before the first true dinosaur ever left a footprint, before the continents resembled anything we know, the Earth was home to a kingdom of life. It was a world ruled not by giant lizards, but by our own distant, bizarre, and terrifying relatives. A world of saber-toothed proto-mammals, of armored reptilian grazers as large as rhinos, and of oceans teeming with ecosystems that had been stable for 100 million years. It was a world that, by all accounts, was successful, mature, and permanent. And then, it vanished. It is known as the Permian-Triassic extinction, but scientists, with a characteristic grim simplicity, call it by another name, the Great Dying. This event is a dark mirror. It challenges our understanding of life itself. It poses the most fundamental question: how do you kill a planet? Not just one species, not one ecosystem, but nearly everything. How do you orchestrate a catastrophe so perfect, so complete, that it erases 96% of all life in the sea and 70% of all life on land? Tonight, we travel 260 million years into the past. We are not just here to witness this apocalypse. We are here to perform an autopsy. We will explore the lost world that preceded it, diagnose the precise cascading planetary illness that caused it, and we will stand in the profound, deafening silence of the ghost world it left behind. This is the story of Earth's darkest hour, and how, from the ashes of near-total annihilation, the world we know today and the long age of reptiles was born. Let us begin by setting our scene. We must first understand what was lost. The time is 260 million years ago, the late Permian period. To stand here is to stand on an alien world that is still our own. The air itself is different. It's thicker, warmer, and holds significantly less oxygen than you are used to. Geochemical models suggest the oxygen content of the atmosphere was perhaps only 16%, compared to our 21% today. Breathing here would be a constant, laborious effort. The sun feels hot, unfiltered, And the plant life is deeply, deeply unfamiliar. There are no flowers, not a single petal, anywhere on Earth. The world is a canvas of greens and browns, unadorned by bright color. There are no grasses. The vast plains we associate with grazing animals do not exist. There are no oaks, no maples, no redwoods. The dominant forests, the great climax ecosystems of this world, are vast, quiet groves of Glossopteris. This is a seed fern, an evolutionary experiment that is neither fern nor conifer, and its broad, leathery, tongue-shaped leaves are the engine of the entire terrestrial food web. These trees are deciduous, but not in the way we know. They likely shed their leaves en masse, creating a thick, slow-to-rot carpet on the forest floor, a carpet that feeds a universe of bizarre insects and decomposers. Alongside them are towering chordates, a group of primitive conifers reaching for the sky. The undergrowth is a dense, damp tangle of sphenopsids, giant tree-like horsetails, and sprawling, complex ferns. This is the flora of the late Paleozoic era perfected. All of this life exists on a single, immense landmass. We call it Pangaea. It is the last time, until our far future, that the world's continents will be fused together. This supercontinent stretches almost from the North Pole to the South Pole, a colossal C shape. This single landmass dictates a climate of profound extremes. The vast, C-shaped interior of Pangaea, shielded by mountains and distance from any oceanic moisture, is a desert of staggering proportions. It is a hyper-arid, oxidized wasteland of red sand, evaporating salt pans, and relentless sun. It is a dead heart, larger than any desert on Earth today. But the edges of the continent, the long coastlines that border the global Panthalassic Ocean and the warm equatorial Paleotethys Ocean, are a different world. They're subject to a massive, continent-spanning monsoon system. For half the year, moisture-laden winds bring torrential, life-giving rains. These regions are lush, wet, and teeming with life. And who rules this world? For most of our history, the answer to that question has always been dinosaurs. But we are tens of millions of years too early for them. The rulers of the Permian are, in a strange and profound way, us. Or rather, our distant ancestors. They are the synapsids. You may know their earliest, most famous ambassador, the Dimetrodon, with its magnificent thermoregulating sail. While it lived much earlier in the Permian, its lineage set the stage. The synapsids were the dominant land vertebrates. They are not reptiles. They are a completely separate, parallel branch of life. The one that would, after hundreds of millions of years of struggle and near extinction, eventually lead to mammals, to us. By the late Permian, the synapsids had evolved into a spectacular, terrifying, and successful array of forms. They were the apex predators. They were the dominant herbivores. They were the small, scurrying insectivores. They had conquered the land. Meet the true king of this lost world, the Gorgonopsian. Imagine a creature the size of a large bear, with the predatory grace of a great cat, but built on a sprawling, powerful chassis. Its name means Gorgon face, and it is well earned. This is Inostranvia, the largest of its kind, found in the northern reaches of Pangaea, in what is now Russia. Its skull is nearly 2 feet long, and from its upper jaw extend a pair of terrifying 6-inch saber teeth. This is not a lumbering, cold-blooded reptile. Its legs, though not fully erect like a mammal's, are positioned more vertically, allowing for a more efficient, sustained stride. This is an active, endothermic, or at least warm-blooded hunter. When it stalks the Glossopteris forests, it is the apex predator, a synapsid killing machine. Its prey is thick-skinned and formidable. The great herbivores of the age are creatures like Scutosaurus. The name means shield lizard. This is an animal the size of a large cow, but built like a walking fortress. It is a periosaur, a group of early reptiles, and its body is covered in bony plates called osteoderms, forming a flexible, powerful coat of armor. They are slow, ponderous, and move in herds, their strange leaf-shaped teeth perfectly designed for shredding the tough Glossopteris vegetation. This is a classic, stable predator-prey relationship. A high-stakes arms race between the saber teeth of the Gorgonopsian and the bony shield of the Scutosaurus. But the true wealth of the Permian, the sheer staggering weight of its biodiversity, is not on land. It is in the ocean. The Paleotethys is a vast, warm, shallow sea, bathed in equatorial sunlight. And in it, life has built ecosystems of a complexity that would not be seen again for 100 million years. The reefs of the Permian are not built by the stony corals we know today. They are vast, intricate, cathedral-like lattices built by bryozoans, tiny moss animals, and brachiopods, the lampshells. These creatures, filter feeders all, create colossal wave-resistant structures that rival the Great Barrier Reef in sheer biological scale. The seafloor is a living carpet. Crinoids, or sea lilies, animals that look like plants related to starfish, wave their feathery arms in the current, forming vast, colorful meadows. Trilobites, the iconic armored arthropods that have existed for over 250 million years, are still here, scuttling in the sediment. In the water column, ammonites, the shelled relatives of squid, hunt and are hunted, their shells a common sight. This is a world in profound balance, an ancient, mature, and deeply stable biosphere. The synapsids rule the land. The brachiopods and bryozoans build the reefs. The trilobites crawl the seafloor. For tens of millions of years, this is the way of the world. It seems eternal, unstoppable, a system too complex, too entrenched, too diverse to ever truly fail. But deep beneath the surface of Pangaea, in the part of the continent we now call Siberia, the planet's mantle is beginning to stir. A plume of superheated rock, wider than a continent, is rising from the core mantle boundary. It is an unstoppable force, a bubble of primordial heat pushing upward at a rate of centimeters per year. And when it reaches the crust, it will not just cause an eruption. It will set the world on fire. The world of the Permian is about to end, and the mechanism of its destruction is not a stone from the sky, but a poison from within. The greatest dying in the history of life is about to begin. To truly comprehend what was lost, we must walk through this vanished kingdom. We must understand its inhabitants, not as fossils in a museum drawer, but as living, breathing creatures,
each perfectly adapted to its time and place. The late Permian was not a primitive prelude, it was a climax, the culmination of the entire 300 million year-long Paleozoic era. Let's land in a specific place, the Karoo Basin of modern-day South Africa. 260 million years ago, this was not a semi-arid scrubland. It was a vast temperate floodplain positioned near the South Pole. It experienced mild, wet summers and long, dark, but not brutally cold winters. It was a world of rivers, lakes, and, above all, forests. The forests here, as in most of the southern hemisphere, are dominated by the Glossopteris tree. This plant is the key. It is the breadbasket of the Permian. It's a deciduous seed fern, and its broad, tongue-shaped leaves form a thick canopy. It's so successful, its fossils are the primary evidence Alfred Wegener used to prove his theory of continental drift. They are found in South America, Africa, India, Antarctica, and Australia. These forests are quiet. No birds sing. The only sounds are the rustle of wind, the skittering of insects, some of them giants, like the Meganeura, a dragonfly with a 2-foot wingspan, and the heavy, rhythmic footsteps of the animals that live here. The dominant herbivores are the dicynodonts. They are everywhere. This single group, a branch of the synapsid line, represents the vast majority of all large land animals. They are the cattle, the sheep, the pigs, and the gophers of the Permian, all rolled into one bizarre, successful package. They are thericeps, the specific group of synapsids that includes our own ancestors, but they look like nothing alive today. Most are squat, barrel-chested animals with a beaked jaws, like a turtle's, and a pair of prominent tusks. These tusks, in both males and females, were likely used for display, for defense, and perhaps for digging up the tough roots and tubers of the Permian flora. The smaller ones, like Diectodon, are compulsive burrowers. They are the size of a small dog, and the karoo is riddled with their fossilized tunnels. These are not simple holes. They are complex, spiral burrows, some over a meter deep, with nesting chambers and side tunnels. These burrows are their refuge. They are a place to escape predators, and, crucially, they are a place to ride out the harsh weather, be it the heat of the day or the long, dark polar winter. This burrowing behavior is a key adaptation. It is a dress rehearsal for survival. Larger dicynodonts, like the hippo-sized Owlocephalodon, graze in the open. They are the great lawnmowers of their time, using their powerful beaks to shear through the tough Glossopteris leaves and fibrous stems. Their massive, barrel-shaped torso indicates a truly enormous gut, a fermentation vat necessary to break down this low-quality, high-fiber diet. They are the mega herbivores of their age. Alongside them, from a completely different lineage, are the heavy infantry, the Perrheosaurs. We met Scutosaurus in the north. Down here in the south, we find creatures like Bradysaurus. The name means slow lizard. Imagine a hippo-sized animal, but wider, lower, and covered from head to tail in bony armor plates, the osteoderms, embedded directly in its skin. Its skull is thick, knobby, and ornate, with bizarre bony flanges sticking out from its cheeks. They are walking tanks, and their defense is their sheer impenetrability. They move slowly, their sprawling legs supporting their immense weight, processing vegetation in their massive gut. Their presence is a testament to the fact that the predators here are powerful enough to require such defenses. And here is that predator, the Gorgonopsid. Let's look closer at Rubegia, a monster from the Karoo. It's larger than a lion, with a massive 18-inch skull. Unlike a reptile, its legs are positioned more vertically, allowing for a more efficient, sustained stride. This is not a lion-weight ambush predator like a crocodile. This is an active pursuer, a warm-blooded killer. Its key weapon is, of course, the saber teeth. These are not for show. The working hypothesis is that they were used for a specific kind of killing. The Gorgonopsid would likely ambush a large Dicynodon or Periosaur, use its powerful neck muscles to drive the teeth deep into the soft, unarmored belly or throat, and then pull back. The teeth were for slashing and causing catastrophic blood loss. The hunter would then retreat and wait for its victim to bleed out. It's a terrifyingly efficient strategy. This is a complex, balanced predator-prey relationship, an arms race that has been stable for millions of years. But the land is not just for synapsids and reptiles. The waterways, the rivers and swamps are the domain of giants from an even older dynasty, the amphibians. These are not the small frogs and salamanders we know. These are temnospondyls. In the Karoo, we find Rhynchus, a 6-foot-long predator that looks like a crocodile-salamander hybrid, its flat skull lined with needle-sharp teeth. But in what is now Brazil, fossils tell of Prosonosuchus. This creature may have reached 9 meters or 30 feet in length. It was a massive, fully aquatic ambush predator, the undisputed king of the rivers. It was the largest amphibian of all time. The Permian is a world where even the amphibians are monsters. Now let's fly north, across the great central desert to the vast boreal landmass of Siberia. The climate here is also temperate, but cooler, with harsher winters. The flora is different. The Glossopteris forests are replaced by vast, dark woods of ancient conifers and giant horsetails. And the fauna is remarkably similar. Here, too, Gorgonopsians rule. This is the home of Inostranzevia, the largest of them all, a polar bear-sized saber-tooth. Here, too, Scutosaurus herds graze, their armor perhaps even thicker. Here, too, Dicynodons burrow and browse. This is a key point. By the late Permian, these ecosystems were globally connected. The same kinds of animals, Gorgonopsid hunters, Periosaur tanks, Dicynodon grazers, were found from the South Pole to the North Pole, a homogeneous, stable, global biosphere, a testament to its own success.
And all this diversity on land is dwarfed by the sheer, staggering biodiversity of the ocean. The land, as varied as it is still recovering from an earlier minor extinction. The sea, however, is at its absolute peak. It is the climax of the entire Paleozoic era. Let's dive into the Paleotethys near the equator. The water is warm, clear, and shallow for hundreds of miles from the coast. This is the Great Reef Belt of the Permian. But these are not our reefs. The organisms that build them are almost all extinct. The primary architects are the bryozoans, moss animals. These are tiny colonial creatures, and they build intricate, lacy skeletons of calcium carbonate. They form delicate branching forests, fans, and mounds. They're joined by stromatoroids, which are strange calcareous sponges that form massive stony pillows. But the most common animal here, the creature that defines the Permian seafloor, is the brachiopod, or lampshell. They look like clams, but they are from a completely different phylum. They are the most common and diverse-shelled animals in the sea, with thousands of species. They cover the seafloor, each one anchored by a fleshy stalk, each one filtering water with a complex, beautiful organ called a lophophore. Their sheer numbers are staggering.
The trilobites are still here. They are the old guard. They have survived for over 250 million years through multiple mass extinctions. They are no longer the dominant force they once were, but they are a vital part of the ecosystem. Specialized trilobite species, crawling through the mud, hiding in the reef's crevices. And waving above it all are the crinoids, the sea lilies. These animals, related to starfish, are rooted to the seafloor by a long stalk, and they filter feed with a crown of feathery arms. Entire meadows of crinoids in vibrant reds, yellows, and oranges cover the submarine landscape. It is a garden of animals.
The predators here are equally strange. Primitive sharks, like the bizarre helicoprion with its spiral saw of teeth in its lower jaw, a biological enigma. And the ammonites, relentless cephalopod predators, are masters of the open water. The entire system is a humming, complex machine of life, built on calcium carbonate. It is a world that runs on shells. This is the world we are about to lose. It is stable. It is diverse. It is global. It is the product of hundreds of millions of years of evolution. It has weathered ice ages and warming events before. It seems permanent, and it is utterly, fatally unprepared for what is coming. The synapsids on land, the brachiopods in the sea, the trilobites in the mud. They are all living on borrowed time. The ground beneath Siberia is beginning to thin. The great plume of mantle rock, a force of unimaginable heat, is just miles below the surface. The fuse has been lit, and the bomb is the planet itself. The Siberian Traps are about to erupt, and the world's intricate, ancient, and beautiful balance is about to be shattered, piece by devastating piece. We have walked through the Lost Kingdom. We have seen the vibrant, balanced, and ancient world of the late Permian. A world ruled by our synapsid cousins, a world of armored grazers and saber-toothed kings. A world with oceans built by organisms that had dominated for hundreds of millions of years. It was a world that seemed permanent. But the universe and our planet operate on scales of time and force that dwarf the tenure of any single ecosystem. The story of life is always, eventually, interrupted by the story of geology. We now turn from the what to the how. We leave the realm of the living and enter the deep, fiery engine room of the planet itself. Our story now moves to its tragic epicenter, the landmass of Siberia, 252 million years ago. This is a vast, rolling landscape of boreal forests, powerful rivers, and deep anoxic swamps. It is cold for much of the year, a high-latitude ecosystem. It is also, geologically, a time bomb. For millions of years, a mantle plume has been rising from deep within the Earth. Imagine this, not as a fire, but as a force. Deep at the boundary between the planet's molten outer core and its solid plastic mantle, 2,900 kilometers beneath our feet, a thermal anomaly begins. A blister of rock, superheated to perhaps 300 or 400 degrees Celsius hotter than its surroundings, begins to swell. This plume is not liquid. It is solid rock, but it is hot and buoyant, like a colossal, continent-sized hot air balloon rising through the denser, cooler mantle. It ascends at a rate of centimeters per year, a journey that takes tens of millions of years.
It is an unstoppable force, a bubble of primordial heat pushing relentlessly, inexorably upwards. As it rises, the pressure on it drops. The rock, still solid but under immense heat, begins to decompress. And as it nears the surface, it crosses a threshold. The pressure is finally low enough for the rock to melt. This is not a small, localized pocket of magma. The head of this plume, as it flattens out against the underside of the Earth's crust, is thought to be over 1,000 kilometers wide. It is melting an area of rock larger than the United States. This molten rock, this magma, is now pushing on the lid.
This is not a single conical volcano like Mount St. Helens or Vesuvius. There is no mountain to build. The pressure is too great, the area too wide. This is a large igneous province, or LIP. The pressure doesn't create a mountain, it creates cracks. Enormous fissures, hundreds of miles long, rip open across the land. They are wounds in the planet's skin. From these fissures, lava does not erupt, it pours. This is flood basalt. It is low viscosity, runny, mafic lava. It flows like water, like a sea of black fire. It floods the landscape in wave after wave, filling valleys, damming rivers, and burying the vast northern forests under a churning, incandescent ocean of molten rock. Any living thing in its path, the Inostranvia, the Scutosaurus herds, the conifer forests, is incinerated. They are instantly erased, entombed in basalt. Each individual flow could be tens, even hundreds of meters thick and cover thousands of square miles. And it doesn't stop. The eruptions are not continuous, but they are relentless. They come in pulses. A flow might last for a decade, flooding a region the size of France. Then it might pause for 1,000 years. Then another fissure opens, and a new flood of fire begins. This pulsing, agonizing process continues for, at minimum, 60,000 years, and perhaps in total for nearly 1 million years. The scale is the key. The Siberian Traps, as we call the resulting rock formation today, would ultimately cover an area of 7 million square kilometers. That is an area larger than Western Europe, larger than the continental United States. The volume of lava erupted is estimated to be between 1.5 and 4 million cubic kilometers. Let that number sink in. 4 million cubic kilometers of magma pulled from the mantle and emplaced on the surface. It is enough lava to cover the entire globe, every continent, every ocean, in a layer 20 feet deep. It is enough to cover the entire United States in a layer a mile thick. This is without question the largest known continental volcanic event in the last 500 million years. The local effect is apocalyptic. The ash and smoke from the burning biomass and the eruptions themselves choke the skies, blocking out the sun over vast regions. This triggers a volcanic winter, a sharp, sudden cold snap. This alone would be a regional catastrophe, a devastating but survivable event. But this is not what caused the Great Dying. The lava itself was not the true killer. The true weapon was invisible. The killer was the gas.
You see, the Siberian Traps were not a simple eruption. The magma did not strike just any piece of crust. By terrible, planet-altering coincidence, the plume rose beneath the Siberian craton. This was one of the thickest, oldest,
and most complex pieces of continental crust on the planet. And it was not empty rock. The Siberian Craton contained the vast Tunguska Basin. This was a geological formation that had, for the previous 300 million years of the Paleozoic, been a massive swamp and shallow sea. It was a basin filled with, tragically, one of the richest carbon reservoirs on the planet. Beneath the surface of Siberia lay massive, untapped deposits of coal, billions of tons of it. There were colossal reservoirs of oil and natural gas trapped in the rock. There were vast, ancient beds of limestone and thick layers of evaporites, salt deposits rich in sulfur and halogens. As the magma plume pushed up, it didn't just erupt through these deposits. A huge portion of the magma, perhaps most of it, pushed into them. It formed a network of horizontal sills, a web of molten rock 1,200 degrees Celsius, spreading out inside the crust. This magma, at over 1,000 degrees, acted like a colossal subterranean forge. It cooked the coal seams. It baked the oil shales. It vaporized the natural gas pockets. This process, called contact metamorphism or thermogenic gas release, was a chemical nightmare on a scale that defies comprehension. It vaporized the coal, releasing truly astronomical quantities of carbon dioxide and methane, two of the most potent greenhouse gases in existence. The methane, in particular, is over 25 times more powerful at trapping heat than CO2. The magma cooked the limestone, calcium carbonate, releasing even more CO2. It baked the sulfur-rich deposits, releasing gigatons of sulfur dioxide, SO2, the primary ingredient for acid rain. It vaporized the salt deposits in the earth, releasing a toxic cocktail of halogens, chlorine, fluorine, bromine. These are incredibly reactive, ozone-destroying gases. This wasn't just a volcanic eruption anymore. This was a planetary-scale industrial pollution event, long before any industry existed. The planet was, in effect, strip mining and burning its own fossil fuel reserves all at once in a single catastrophic pulse.
We know this is true. The evidence is not just in the lava, it is written in the chemical signature of the rocks all over the world. In sedimentary rocks from Italy, from China, from South Africa, layers that span the Permian-Triassic boundary, scientists find a sudden, dramatic spike in light carbon, or carbon-12. Life, be it a plant, a microbe, or an animal, prefers to use the lighter C12 isotope of carbon to build its body. Heavy carbon-13 is left behind. This means that all organic matter, biomass, coal, oil, and methane, is overwhelmingly rich in light C12. That sudden, global, negative spike in the carbon isotope record is the smoking gun. It is the geochemical signature of a truly massive, mind-bogglingly fast injection of dead organic carbon into the planet's atmosphere. It is the fingerprint of those vaporized Siberian coal and gas fields. Other chemical fingerprints add to the indictment. At the boundary layer, scientists find a massive spike in mercury. Mercury is a telltale trace element released by volcanism. They find microscopic fly ash spherules, the tiny condensed droplets of burned coal, identical to the pollution from a modern, unfiltered coal-fired power plant. They find a spike in nickel and other metals, characteristic of the mantle plume's specific magma. The evidence is overwhelming. The case is closed. The Siberian Traps were not just an eruption, they were a system. A perfect storm of geological coincidences. A mantle plume, the largest in 500 million years, striking a section of crust that just so happened to be the world's largest, most volatile fossil fuel reserve.
How much carbon? The estimates are staggering, and they are the subject of intense scientific debate. But the consensus points to a release of at least 10,000 gigatons of carbon, and perhaps as high as 30,000 gigatons injected into the atmosphere in a geological instant. For context, humanity's entire industrial activity, from the first steam engine to today, has released about 500 gigatons. The Siberian Traps may have released 60 times that amount, and in a fraction of the time. The initial volcanic winter from the ash would have been brief, lasting only decades. But it was quickly and permanently replaced by a far more lethal mechanism. The planet's atmosphere was now saturated with greenhouse gases. Atmospheric CO2 concentrations, which had been at a stable, livable 400 or 500 parts per million, soared. They rocketed to 3,000, 5,000, perhaps as high as 8,000 parts per million. The Earth's thermostat was not just broken, it was strapped to a furnace. A runaway greenhouse effect was now inevitable. The planet was about to enter a fever, a hyperthermal event that would last for thousands of years. The Siberian Traps were the catalyst. The fire was lit. The poison was in the air. But the dying would be slow, methodical, and global. The cascade of disaster was just beginning. The land would die first, and then, in a truly horrifying chemical chain reaction, the oceans would follow. The gun has been fired. The Siberian Traps are in full eruption. A million-year-long flood of fire is injecting gigatons of poison into the planet's fragile atmosphere. But the death of the world was not instantaneous. It was not a singular, clean event. It was a cascade, a chain reaction of catastrophes where each disaster triggered the next, a series of dominoes falling in slow, agonizing succession. We must now trace this cascade step by step. We must follow the poison as it seeps from the sky into the soil, from the soil into the sea, and from the sea back into the air. This is the anatomy of the planet's greatest sickness. Mechanism 1: the acid scourge. The first wave of death comes not from heat, but from the sky itself. The Siberian eruptions, from cooking the sulfur-rich deposits in the crust, are belching gigatons of sulfur dioxide, SO2, into the atmosphere. In the upper atmosphere, this SO2 combines with water vapor, light, and oxygen. It forms H2SO4, sulfuric acid. At the same time, the magma is vaporizing ancient salt deposits, releasing a toxic cocktail of halogens, chlorine and fluorine. These gases are hyper-reactive. In the stratosphere, they begin a catalytic cycle, tearing apart the planet's ozone, O3, layer. The world is now facing a two-pronged atmospheric assault. The first is acid rain, and we are not speaking of the slightly acidic rain that troubles our modern cities. We are talking about a corrosive downpour of sulfuric and hydrochloric acid. Geochemical models based on the sheer volume of SO2 released suggest this rain could have had a pH of 2.0, the pH of lemon juice or vinegar. This acid rain falls relentlessly, month after month, year after year, all across the northern hemisphere and eventually the globe. It chemically burns the leaves of the Glossopteris forests. It defoliates the canopies, shutting down photosynthesis.
Second assault is radiation. With the ozone layer shredded by halogens, the Earth's primary shield against the sun's most lethal ultraviolet radiation, UVB and UVC, is gone. The surface of Pangaea is now blasted with high-intensity UV radiation. This radiation shatters the DNA of living organisms. For plants, it's a death sentence, causing mutations and halting their ability to reproduce. For animals, it causes blindness, skin lesions, and cancers. The world is simultaneously being burned by acid from above and sterilized by radiation from the sun. The great forests of Pangaea, from Siberia to the Karoo, die. They are burned, poisoned, irradiated, and starved. The foundation of the entire terrestrial food web has been vaporized. The great herbivores, the pariasaurs and the dicynodons that relied on this vegetation starve. Their armored hides and powerful beaks are useless against a world with no food. Their carcasses litter the barren, silent plains. And the apex predators that hunted them, the mighty Gorgonopsians, starve soon after. Their saber teeth, the pinnacle of Permian evolution, are a specialization for a world that no longer exists. The entire complex terrestrial ecosystem, the magnificent kingdom of the synapsids, collapses in a global famine. We see this death, this absence, in the rock record. Geologists call it the coal gap. For millions of years, the Permian is full of thick, rich coal seams, the compressed, fossilized remains of those vast, healthy forests. Then, suddenly, at the boundary, the coal stops. And for the next 5, perhaps as long as 10 million years, almost no coal is formed anywhere on Earth. The forests were gone. What replaces them? The rock record tells this story too. Immediately after the plant die-off, we find a fungal spike. In boundary layer rocks worldwide, the fossil pollen from trees vanishes. It is replaced by a single, thin layer composed almost entirely of fungal spores. This is the signature of a world covered in rot. With the trees dead, fungi and other decomposers inherited the earth. They were the only things that could thrive in this global graveyard. They feasted on the trillions of tons of dead wood and the decaying animal life. The landscape is reduced to a gray, moldy, silent wasteland. The air is thick with the smell of decay. The land, for all intents and purposes, is dead. The acid rain and the volcanic winter were the opening acts. They were swift, violent, and destructive. But as the ash and aerosols settled out of the sky, the true, long-term killer took hold. The Siberian Traps were not just injecting sulfur, they were injecting carbon dioxide and methane. The methane, CH4, released from the cooked gas fields would have been a catastrophic short-term warmer. But it oxidizes into CO2 in just a few decades. The CO2, however, is permanent. It stays in the atmosphere for thousands of years. The planet's carbon cycle is overwhelmed. The atmosphere is now saturated with greenhouse gases, trapping the sun's heat. The Earth's thermostat is broken. The planet enters a hyperthermal state, a runaway greenhouse effect. How hot did it get? We can read the planet's ancient thermometer. The evidence is locked within the fossilized teeth of tiny eel-like creatures called conodonts and in the oxygen isotopes of minerals. The data is shocking. Global average temperatures soared. The average temperature of the planet may have increased by 10 to 15 degrees Celsius. This is not a gentle warming. This is a planetary fever. The polar regions, once temperate and cool, became subtropical. And the tropics? The tropics became lethal. Sea surface temperatures in the equatorial Paleotethys Ocean, which should have been a balmy 25 or 28 degrees, skyrocketed. Our best models based on this oxygen isotope data suggest they reached a staggering 40 degrees Celsius, over 104 degrees Fahrenheit. This is not warm. This is a hot tub. It is biologically unsurvivable for almost any complex marine animal. Fish, mollusks, even bacteria. Their proteins literally denature. The ocean's equator, the cradle of biodiversity, becomes a lethal zone, a shimmering, sterile, overheated soup. On land, the effect is just as brutal. The heat, combined with the extreme aridity of the Pangaean interior, turns the entire center of the continent into a blast furnace. Any lingering hardy plants are baked out of existence. Life on Earth is now compressed into two temperate, survivable refugia near the North and South Poles. The vast majority of the planet, from the tropics to the mid-latitudes, is simply too hot to support complex life. The world is being baked. And the oceans? The oceans are where the true apocalypse unfolds.
The land lost 70% of its species. It was a catastrophe. The ocean will lose 96%. This is where the great dying truly earns its name. The mechanism is a three-act tragedy. A chemical cascade that turns the cradle of life into a poisoned tomb. The ocean is the planet's great carbon sink. It is absorbing vast quantities of that atmospheric CO2. But there is a limit. As the CO2 dissolves, it forms H2CO3, or carbonic acid. This is the same reason a can of soda is fizzy and acidic. But now it is happening on a global, oceanic scale. The pH of the entire ocean surface begins to drop. The sea becomes corrosive. Remember the Permian reefs? The brachiopods,
the bryozoans, the crinoids, the trilobites, the ammonites, the plankton at the base of the food web, the foraminifera. Their entire way of life was built on one mineral, calcium carbonate. They build their shells, their stalks, their intricate skeletons from this mineral, pulling carbonate ions directly from the seawater. But in an acidic ocean, two things happen. First, the carbonate ions they need to build their shells become scarce, as they are stolen by the excess hydrogen ions. Second, the water itself becomes corrosive, undersaturated in calcium carbonate. For these organisms, it is like trying to build a house while the bricks are dissolving in your hands. The mortar won't set, and an acid storm is eating the foundation. They cannot build, they cannot grow, they cannot reproduce. Their larvae, tiny and unshelled, dissolve in the water. The adult shells become thin, pitted, and weak. The great, ancient, cathedral-like reefs of the Permian simply die. They crumble into ooze. The trilobites, the ultimate survivors, the icons of the Paleozoic era that had weathered 250 million years and multiple mass extinctions, are wiped out forever. The brachiopods and crinoids, which had dominated the seafloor for an entire era, are decimated. 99% of their species vanish. The ocean's entire architecture, the foundation of its food web, collapses.
The second blow, happening at the same time, is suffocation. A healthy ocean breathes. It has lungs. This process is called the thermohaline circulation. Cold, dense, oxygen-rich water sinks at the poles and circulates around the globe, delivering oxygen to the deep sea. But in the Permian hyperthermal, the poles are warm. The water is no longer cold. It is no longer dense. It no longer sinks. This global conveyor belt of oxygen stops. The oceans become stagnant. They stratify. A hot, acidic, but slightly oxygenated layer forms on top, but beneath it, the deep ocean is cut off. It is no longer receiving fresh oxygen from the surface. At the same time, all the rotting organic matter from the dead reefs, Act A, and all the dead vegetation washing off the land, Mechanism 1, is sinking into this stagnant deep water. Bacteria, aerobic bacteria, bloom to consume this massive feast of rot. And in the process, they consume all the remaining dissolved oxygen. They use it all up. The oceans begin to suffocate from the bottom up. Vast anoxic zones, regions with zero oxygen, spread from the deep sea, rising higher and higher, pushing into the shallows. Any creature that cannot flee to the paper-thin surface layer, fish, ammonites, crustaceans, is asphyxiated. The oceans are turning into vast, stagnant, poisoned ponds. And now, the final, horrifying twist. In this new, oxygen-free ocean, a new form of life thrives. Life that last dominated the Earth billions of years ago. These are anaerobic bacteria, microbes that do not breathe oxygen. Instead, they breathe sulfate, SO4, which is abundant in the ocean. These sulfate-reducing bacteria flourish in the anoxic ocean. They multiply by the trillions upon trillions, consuming the endless rain of rotting organic matter. And as they metabolize, they excrete a waste product, a gas, hydrogen sulfide, H2S. This is a highly toxic gas. It is the smell of rotten eggs. It is a potent poison to almost all aerobic life, life that breathes oxygen, like us. It shuts down the mitochondria in our cells. These bacteria bloom, unchecked, in the deep ocean. They turn the entire deep sea into a toxic cauldron of hydrogen sulfide. Geologists call this an eugenic ocean. The water itself, saturated with this bacteria and the chemicals they produce, may have turned a ghoulish, oily pink or purple. It is an ocean from a primordial nightmare. And this toxic H2S saturated water does not stay in the deep. The anoxic eugenic zone continues to rise until it breaks the surface. The ocean, the cradle of life, has become the planet's poison gland. It burps. The hydrogen sulfide gas, now at lethal concentrations, bubbles out of the ocean and into the atmosphere. It kills any remaining life on the coasts. It poisons the already struggling survivors on land. And in a final, terrible feedback loop, the hydrogen sulfide gas itself also attacks the ozone layer, just as the halogens did, worsening the radiation problem. It's a feedback loop of death, amplifying its own lethality.
This is the kill mechanism, a perfect, interconnected storm. The acid rain and radiation sterilize the land. The runaway heat bakes the continents. The global food web collapses into rot. The oceans acidify, dissolving the reef builders. The oceans suffocate, turning stagnant and anoxic. And finally, the seas themselves become a source of poison gas, killing what little is left. This is how you kill 96% of a planet's species. This is the Great Dying. The cascade is complete. The world of the Permian is gone.
Silence. The fever has broken. The final pulse of the Siberian Traps has quieted. The acid rain has ceased. The hydrogen sulfide, for now, has settled back into the stagnant depths. But the world it has left behind is a shell, a charnel house. We are now in the early Triassic, perhaps a few 100,000 years after the peak of the extinction pulse. The silence is absolute. It is the most profound, deafening silence this planet has known in 300 million years. This is the ghost world. The planet's biodiversity has been reset. The intricate Baroque complexity of the late Permian is gone, as if it were a dream. It has been replaced by a barren, simplified, and profoundly broken world. The land is a sterile desert. The great Glossopteris forests, the engine of the southern hemisphere, are gone. The northern conifer woods are gone. They have been replaced by fungal woods, landscapes of rot, which themselves have now faded. The first hardy disaster flora is beginning to reclaim the land, but it is not a forest. It is a sparse, desperate scrubland. Weedy, quill-like plants like pluralmea and the strange, root-like isoetalase. These are the ecological equivalent of weeds pushing up through the rubble of a bombed city. They are survivors, not conquerors. Even the face of the planet has changed. The rivers themselves are broken. In the Permian, rivers meandered. They carved deep looping S-curves through the landscape. Why? Because their banks were held firm by the deep, complex, tangled root systems of the Glossopteris forests. Plants anchored the land. Now, in the early Triassic, the forests are gone. There are no roots to hold the soil. When the rains come, and they are chaotic, furious downpours on this unstable planet, the water shears the land away. The sediment and ash from the dead world chokes the river channels. The rivers lose all structure. They become braided streams, wide, shallow, messy, chaotic webs of water that constantly shift their course. We can see this in the rock record. The beautiful meandering river deposits of the Permian abruptly stop and are replaced by the chaotic, messy gravel beds of braided streams. It is a scar on the planet's surface, a geological signature of the death of all plants. The Earth itself is bleeding soil into the sea.
But this world is not entirely empty. Life, in its desperation, has a few very strange survivors, and one in particular has inherited this broken Earth. Meet Lystrosaurus. It is a dicynodont, a member of the great synapsid family that ruled the Permian, but it is one of the very few to make it through the fire. It is not impressive. It's about the size of a pig, with a squat, barrel-chested body, sprawling forelimbs, and more upright hind limbs. Its face is a bizarre, shortened turtle-like beak. Its only teeth are a pair of prominent tusks. It is a herbivore. And in the early Triassic, it is everything. In the fossil beds of the Karoo Basin in South Africa, the story is written in stone. Before the boundary, the rock is teeming with diversity. Dozens of species, Gorgonopsians, Parasaurs, Theracephalians, multiple families of dicynodonts, a complex, vibrant ecosystem. Then you cross the thin, red line of the extinction, and in the layers just above it, 90% of all vertebrate fossils found are this one animal, Lystrosaurus. This is the Lystrosaurus zone. It is a world of one, a planet dominated by a single, hardy disaster taxon. The apex predators are gone. The large herbivores are gone. The medium-sized herbivores are gone. There is only Lystrosaurus. How did it do it? How did this one seemingly unremarkable pig lizard survive when the mighty Gorgonopsians and the armored Parasaurs perished? The answer lies in a perfect combination of lucky adaptations for an unlucky time.
First, it was a burrower. Like its smaller Permian ancestors, Lystrosaurus dug tunnels. We have found the fossilized casts of its burrows. They are deep, extensive, and often have a resting chamber at the bottom. When the hyperthermal heat baked the surface to 104 degrees, Lystrosaurus was underground, where the temperature was stable. When the acid rain fell, Lystrosaurus was underground. When the hydrogen sulfide gas burped from the oceans and poisoned the coastlines, Lystrosaurus was underground. It could seal itself off, perhaps in a state of torpor, a deep hibernation, and simply wait. It could wait for weeks or months for the worst of the surface conditions to pass. It had a built-in apocalypse shelter. Second, its lungs. The air of the early Triassic was a toxic, low-oxygen brew.
The coal gap and the death of ocean plankton meant that oxygen production had cratered. The atmosphere was thin, hypoxic, and still choked with CO2 and other volcanic gases. Lystrosaurus, with its massive barrel-shaped chest, appears to have evolved unusually large, powerful lungs. It was uniquely adapted to breathe this bad air. It could thrive, or at least survive, in conditions that would have caused other animals to asphyxiate. Third, its diet. It was a generalist. It didn't need the lush, complex glossoparous forests. It was a weed eater. Its powerful beak was perfectly designed for shearing the tough, fibrous disaster flora, the hardy weeds, roots, and tubers that were the first to reclaim the barren land. It ate the few things that could grow, and with no predators and no competitors, its population exploded. So this one tough, burrowing, large-lunged generalist synapsid, this pig lizard, became the most successful vertebrate on the planet. Its herds spread from South Africa to Antarctica, to India, to Russia, to China. For a few million years, Earth was the planet of Lystrosaurus. It's a chilling vision of success, a world without predators, a world without competition, a world without diversity. Just Lystrosaurus. Everywhere.
The oceans are just as bleak. The magnificent reefs of the Permian are gone, reduced to limestone rubble. The complex food webs are gone. The water is warm, acidic, and in the depths, still murderously anoxic and eugenic. This, too, is a world of disaster taxa. The seafloor is not covered in brachiopods and crinoids. It is covered in vast mats of simple, thin-shelled bivalves. The most famous is Clauria. This paper pecten or paper scallop could tolerate the toxic low-oxygen water. Like Lystrosaurus on land, it was a hardy generalist, and for a time, it and a few other hardy clams were the only complex animals on vast stretches of the seafloor. The predators? A few ghost lineages of sharks barely clinging on. Some ammonites survived, but just barely. The survivors were tiny, simplified micro-ammonites, their shells lacking the ornate complexity of their Permian ancestors. They were reset evolutionarily. The great trilobites are gone forever. The brachiopods and crinoids are 99% extinct, clinging on only in the most isolated, deep-water refugia. The ocean is an empty, silent, stagnant void. This ghost world is perhaps the most terrifying chapter of the story. It reveals the true cost of mass extinction. It is not just death, it is the loss of complexity. The intricate, beautiful machine of the Permian, built over 300 million years of the Paleozoic era, was broken. The predators were gone. The reef builders were gone. The forest makers were gone. The niche specialists were gone. Life had been reduced to its foundations. A few weeds, a few clams, and one very, very successful pig lizard. It would take millions of years for the world to recover. The planet was so profoundly damaged, chemically and biologically, that it took 5 million, perhaps 10 million years for ecosystems to even begin to rebuild their former complexity. This was the longest, slowest recovery from any extinction in Earth's history. The planet was in a profound state of ecological shock. But in this emptiness, in this world of burrowing generalists, something new is stirring. The great synapsids, our relatives who had ruled the Permian, were decimated. Lystrosaurus was an exception, a dead man walking, a lineage that would prosper in the chaos and then vanish a few million years later. The Gorgonopsians were gone forever. The great Periosaurs were gone. This left a power vacuum, an ecological vacuum on a planetary scale. All the jobs that the synapsids and their contemporaries used to do, the job of apex predator, the job of large herbivore, the job of medium-sized grazer, the job of small fast runner, were now open. The stage was empty. And in the shadows of the early Triassic, in the margins of the Lystrosaurus empire, another group of survivors was beginning to experiment. A group that had been minor, small-bodied, and overlooked in the Permian. They were the archosaurs, the ruling reptiles. They were the ancestors of crocodiles, of pterosaurs, and of dinosaurs. The Great Dying had been the end of the synapsid world. It was their apocalypse. But in clearing the board, it had inadvertently set the stage for the next great dynasty. The devastation of the Permian-Triassic boundary was the terrible, fiery crucible that would forge the age of reptiles.
The world did not end, but the world of the Permian, the 300 million year-long story of the Paleozoic era, was over. We are now in the early Triassic, and the planet is in a state of profound, agonizing convalescence. The recovery from the Great Dying was not a renaissance. It was not a green shoot of rapid renewal. It was the longest, slowest, most grueling recovery in the history of life. It would take 10 million years for the planet's ecosystems to even begin to resemble their former complexity. Let that number sink in. 10 million years. Our entire human lineage, from our split with the chimpanzees, is only 7 million years old. The planet was so profoundly broken, so chemically scarred, that it took longer than the entire span of human evolution just for forests to return. Why so long? Because the planet's fundamental operating systems were broken. The carbon cycle was in chaos. The Siberian eruptions hadn't just stopped. They sputtered, flared, and ebbed, continuing to pulse greenhouse gases into the air for perhaps 1 million years. The planet was trapped in a feedback loop. The heat, the stagnant oceans, they weren't healing. The geochemical record shows that the early Triassic was a time of false dawns. A small ecosystem might establish itself. A new fern-like plant might take hold. And then another hyperthermal event. Another pulse of CO2 from the still healing Earth or methane from the anoxic seas would spike the temperature and the new ecosystem would collapse. Life would take 2 steps forward and 1 devastating step back. The planet was trapped in a 5 million year-long fever dream. But in this broken world, in the margins of the Lystrosaurus empire, the true survivors were beginning to lay the groundwork for the future. Our relatives, the synapsids, were not entirely gone. Lystrosaurus was a dead-end branch, but another group had clung on, the cynodonts. Meet Thrinaxodon. It's the size of a cat. It has complex, differentiated teeth, incisors, canines, and molars. It may have had whiskers. It may have had fur. And like Lystrosaurus, it was a burrower. We have found its fossilized tunnels, its body curled up inside, sometimes with its young. This creature is our ancestor, or very close to it. The Great Dying was the event that hammered our lineage into the shape it would hold for the next 150 million years. It taught our ancestors a lesson. The world is dangerous. The day is for monsters. Safety is underground. Safety is in the dark. The cynodonts adopted the nocturnal niche. They became small, warm-blooded, hyper-metabolizing, hyper-aware creatures of the night. They were no longer the rulers. They were the survivors. This is our origin story, hiding in the rubble of a dead world.
But there was another group of survivors, a group that had been small and insignificant in the Permian. They too had weathered the storm. Perhaps they had more efficient lungs. Perhaps they had a better tolerance for heat and aridity. They were the archosaurs, the ruling reptiles. And as the planet stabilized, as the Triassic dawns, these two groups of survivors, the nocturnal, burrowing synapsids and the adaptable, rising archosaurs, stood on the shore of a vast, empty ecological ocean. All the jobs of the Permian were vacant. The job of large herbivore, left by the parasaurs. The job of apex predator, left by the Gorgonopsians. The job of river monster, left by the giant amphibians. The Triassic period, the first chapter of the Mesozoic era, would be a 30 million year-long war for these vacant jobs. It was a war to define the future of life. And it was a war our ancestors would lose. The ghost world is fading. After 10 million years, the forests have returned. Not the Glossopteris forests, but new, hardier forests of conifers, ferns, and cycads. The coal gap ends. In the oceans, new forms of plankton have evolved. And, critically, a new type of reef builder has appeared, the scleractinin corals. These are the stony corals that build all modern reefs. They take over the job that the brachiopods and bryozoans had abandoned and begin to build new, complex habitats. The ocean is finally coming back to life. And on land, the reign of Lystrosaurus is over. New, more specialized herbivores have evolved to replace it, and new predators have evolved to hunt them. But who were these new rulers? They weren't the dinosaurs. The archosaurs had radiated. They split into two great competing branches. The first branch was the Pseudosuchia, the crocodile-lined archosaurs. And in the Middle Triassic, they won. They were the first to fill the vacuum. They became the new apex predators. Meet Erythrosuchus, the red crocodile. A 16-foot-long predator with one of the largest skulls, relative to its body, of any animal ever. It was the new Gorgonopsian. They were replaced by even more terrifying predators, the Rausuetians. This is Saurosuchus. 25 feet long, a fast, powerful, land-based predator. It was the undisputed apex predator of the late Triassic. It hunted everything. The Pseudosuchians took the other jobs too. The role of armored tank, left by the Periacosaurs, it was filled by the Atosaurs, reptiles covered in bony plates with pig-like snouts. The role of river monster, left by the giant amphibians, it was filled by the Phytosaurs, creatures that looked and lived exactly like modern crocodiles, a perfect example of convergent evolution. So, where are the dinosaurs? They were here. They were the other branch of archosaurs, the Avemetatarsalia, the bird-line archosaurs. But they were losing. While the crocline archosaurs were evolving into giant predators and armored tanks, the bird line was evolving for speed, for agility. They were the underdogs. They were small, bipedal, and fast, creatures like Marsupials. They were the deer and foxes of this Triassic world, living in the margins, snatching insects and small lizards, and running for their lives from the giant Rausuicians. From this lineage of fast bipedal runners, around 240 to 230 million years ago, the first true dinosaurs appeared. This is Uroraptor, the dawn plunderer. It's 3 feet long. It's a lightweight omnivore. This is Herrerasaurus, a bit bigger, 10 to 20 feet long, a significant predator, but still not the apex predator. It lived in a world where Saurosuchus was king. For 20 years, this was the status quo. The Triassic was not the age of dinosaurs. It was the age of Pseudotsuchians. It was the age of the crocodile's weird cousins. The dinosaurs were a minor background group, interesting and fast, but confined to the margins. Our synapsid ancestors, the cynodonts, were tiny, nocturnal, and hiding in their burrows. If you were a betting person in the late Triassic, you would have bet on the crocline. They were bigger, stronger, and occupied every major niche. The dinosaurs were a failed experiment. And then, 201 million years ago, the planet did it again. Pangaea, the supercontinent that had defined this entire era, was finally, violently ripping apart. The landmass was stretching, and as it stretched, it tore. A new set of colossal fissures opened in the crust. A new large igneous province flared to life. This was the Central Atlantic Magmatic Province, or CAMP. It was the exact same story. As North America ripped away from Africa, lava flooded an area of 11 million square kilometers. It was even larger than the Siberian Traps. And once again, the magma cooked coal and gas fields. Once again, gigatons of CO2 and methane flooded the atmosphere. Once again, the planet was plunged into a runaway greenhouse effect. Once again, the oceans acidified. It was a double tap, a second brutal mass extinction, just as the world had finally recovered from the last one. This is the Triassic-Jurassic extinction.
This second extinction was not as powerful as the Great Dying, but it was just as selective. And this time, the victims were different. The giant amphibians were wiped out. The phytosaurs were wiped out. The adiosaurs were wiped out. The giant Rauisuchians, the apex predators of the world, were wiped out. The entire croc line of Pseudotsuchians, the dominant rulers of the Triassic, were gone. Our synapsid ancestors, the cynodonts, hiding in their burrows, they were battered, but they survived. The true crocodilians, small and aquatic, also survived. And the dinosaurs. The dinosaurs survived. Why? The leading theory is their lungs. Dinosaurs and their bird descendants have a one-way respiratory system with air sacs. It is hyper-efficient at extracting oxygen from the air. In the poisoned, low-oxygen, high-CO2 atmosphere of the Triassic-Jurassic extinction, this was their superpower. While the great Rauisuchians, with their less efficient lungs, were asphyxiating, the dinosaurs could breathe. Their high metabolism, their mesothermy,
which had kept them fast and active, now helped them survive the chemical warfare of a dying atmosphere. They were, perhaps, pre-adapted for an apocalypse. The board was cleared, again. But this time, the dinosaurs were the only players left in the game. The ecological vacuum was theirs and theirs alone. The Jurassic period opened, and the dinosaurs, the lucky, apocalypse-ready survivors, radiated. They exploded into every vacant niche. The job of apex predator was taken by theropods like Dilophosaurus. The job of large herbivore was taken by the first giant sauropods. The age of reptiles had begun, but it was not a foregone conclusion. It was not a destiny. It was an accident. It was born from the ashes of the greatest catastrophe life has ever known, and then sealed by a second, unrelated catastrophe that just happened to kill all of an animal's competitors. The dynasty of the dinosaurs was built on the ruins of two worlds.
We have traveled to the edge of annihilation and back. We have stood in the shadow of the Gorgonopsians, breathed the toxic air of a dying world, watched the oceans turn to purple poison, and walked the silent fungal plains of the ghost world. We have witnessed the planet's greatest sickness. The Great Dying is a story of almost incomprehensible scale, a 96% loss of marine life, a 70% loss of terrestrial life. It is the closest our planet has ever come in the entire history of complex life to a total sterilization. It is a testament to the profound, terrifying fragility of complex systems. It reveals that an entire global biosphere, an intricate masterpiece built over 300 million years, can be undone. It can be broken by a single catastrophic geological event, a terrible coincidence of fire and fuel. The Great Dying teaches us that the world we know is not a given. It is a state, a temporary arrangement of chemistry, temperature, and biology. The intricate web of life, which seems so robust, is entirely dependent on a stable foundation. And when that foundation cracks, the world falls. The reefs of the Permian, built by brachiopods and bryozoans, vanished. The trilobites, survivors of 250 million years, were erased. The synapsids, the great land dynasty that was, by all rights, destined to rule, were deposed.
And yet, the story of the Great Dying is also, perhaps, the greatest story of resilience the planet has ever told. Life, as a concept, did not end. In the deepest burrows, in the most isolated, oxygenated refugia, a few hardy, desperate survivors clung on. Lystrosaurus, the pig lizard, waiting out the firestorm underground. Chloria, the paper clam, filtering a toxic sea. And our own ancestor, the tiny, furry Thrinaxodon, curled in the dark, learning the lessons of the night. From those few battered survivors, the 4% of marine life and 30% of land life, the world was rebuilt. The planet was repopulated. Life, it seems, can endure almost anything, but the world it builds is fragile. The recovery took 10 million years. 10 million years for the forest to return. 10 million years for the reefs to regrow. 10 million years for complexity and diversity to re-emerge from the rubble. The Great Dying is a story from deep time, a ghost from a 250 million-year-old past. but its echoes are deeply, profoundly relevant. Its mechanisms are not alien. They are horribly familiar. A massive, rapid injection of greenhouse gases into the atmosphere from the burning of ancient buried carbon, a runaway greenhouse effect, global warming on a planetary scale, ocean acidification dissolving the shells of marine life, ocean anoxia creating vast, suffocating dead zones. The Siberian Traps were a natural catastrophe. Today, we are replicating those same mechanisms. We are, in our own way, a geological force. The rocks of the Permian-Triassic boundary are not just a record of death. They are a warning. They are a case study written in stone of what happens when a planet's carbon cycle is broken rapidly and violently.
But ultimately, the story of the Great Dying is a story of connection and of chance. It connects the fire deep within the earth to the chemistry of the sky. It connects the sky to the ocean. It connects the ocean to the land. It connects the Gorgonopsian to the Lystrosaurus. It connects the failure of our synapsid ancestors to the lucky, improbable, apocalypse-driven rise of the dinosaurs. And it connects the fall of those dinosaurs 150 million years later to the rise of our own lineage, the mammals who finally came out of the dark. We are all survivors. We are all the children of catastrophe. The earth is old, and it has seen worlds end, but it has also seen them begin again. The silence of the ghost world eventually gave way to the chaos of the Triassic. The age of synapsids gave way to the age of reptiles, and the age of reptiles gave way to the age of mammals. The planet abides, and life, no matter how broken, how close to the edge, finds a way. It is a story of endings and a story of new beginnings, written in stone and echoed even now in our own breath. Thank you for joining us on this journey through the Great Dying.